got some work done here early, I may be able to actually start the next job a little bit early. Let's see if this is done now. Here we go. And there it is. It's now batch critical. Okay, right here. So that particular process, when a scheduled time came up, it had already gotten 3 minutes done. But this process actually takes less than 3 minutes to work. There were 25 seconds there where it was thrashing because it was running in the opportunistic band as a B. And it'd get into the CPU, load data into cache, and then get kicked out before it could actually use the data. But this is actually less than a 3-minute job, and it's inefficient thrashing on that secondary cache. So right at 11:01:31, basically it looks like a tight window here, but we went from B right here, B, and here's BC now. And at that time the date was 11:01:31. It happened right, there's 11:01:30. So there's a slight 1 second window where the PS might not have been completely quick enough to catch that window within that 1 second. So this is showing opportunistic miser, and that's what just happened with us. That code was in the B mode and able to run a little bit before it actually went critical. In fact, in the slide we were able to see it got 3-some minutes done before it actually ran in batch critical. Now I already had 3 minutes 27 seconds that were executed in the opportunistic mode before I went critical. Out of curiosity now, those are all done. ACCOM-N on the codes. And one of them ran at 288 seconds. I got another here at 312, 292, 300, 308. It's all the same amount of work. They all did exactly the same number of floating point computations. But the amount of time it took to do them varied because part of that time is my secondary cache misses. Okay. So dispatches jobs that have been scheduled to run, terminates jobs that exceeded their deadlines. I did not exceed my deadline because I overestimated service time requirements. I'll schedule the jobs on any idle CPUs. Miser does not say which CPU number you're locking down into. Okay. Miser's CPU set does, but regular Miser, you simply say, give me some CPUs. It doesn't determine which ones. And that's the futures that they want on the list. It has an ordered list of batch jobs, and that ordered list was miser_jinfo. And I can, again, do I've got a miser_qinfo all script that I use that basically goes through now and does a PS and tells me I got 1, 2, 3, 4 code 2s that are still running, and they're going to run from 11:03 to 11:08. And I'm at 11:04 now, so they should all be batch critical. So I should have 4 code 2s, and there they are. They're all batch critical, and guess what? Jeff is going to get beat up because I can take CPUs away from him now. Because I'm in the batch critical band, and he's in the timeshare band. But he's also up the NICE a little bit. He's running at a NICE of 10 rather than 20. But that still doesn't matter because I'm in a higher priority class. They're going to catch me in my class before they go to the timeshare. And some of those code 2s are now finishing up. Jobs are ordered by urgency, time remaining until a job start time. And then before a job start time, the kernel may run it opportunistically. After the job start time, the job is referred to as critical and has priority over its assigned resources. It will never have pages stolen from it in batch critical mode. It's acting like a Cray real memory machine with no swapping. But again, you cannot oversubscribe it. That was by CPUs, but it's also by memory. I can't have Miser use more memory than is physically on the system. So Cray sites that run 20 times more work than they have physical memory would not be able to use Miser. And I've been trying to reset Cray customer expectations in this area and say, don't run these things like a Cray. Don't oversubscribe anything. Don't swap all the time. A lot of that sets them up for Miser. Once they understand you don't oversubscribe these machines, then they're ready psychologically to use something like Miser, where you cannot oversubscribe it. And again, it terminates jobs that run too long past their scheduled in time. You will get killed. So it's a scheduling system. It's simply another way of isolating the batch from the interactive. Now when I'm batch critical, the interactive cannot steal from me. So the life cycle is just trying to show here, I start off, I submit as timeshare. Basically, miser underscore submit makes the sysmp system call and gets miser attributes, permissions from the kernel. And when it comes out, it would then have inherited the miser attributes from the kernel. So then it waits for the user level scheduler to kick up, becomes batch, gets put on the batch queue, figures out when the current time is equal to the start time that I'm scheduled is critical. Otherwise, it's just going to get normally dispatched and preempted based upon the load on the system. Once it's batch critical, it's bound to the CPU, and again, it's going to be running. It can still get preempted by real-time daemons, NFS daemons, stuff like that. And if the current time equals in time, then I get killed. And hopefully I estimated correctly. Keep in mind, I may underestimate it because I ran it in a load level, and if I run it again and it's got high cache thrashing, I may miss it. If the service times aren't repeatable, how can I tell it what I need? Okay. So miser submit, the job is submitted to miser, converts the job to batch by making the sysmp system call. If a CPU is idle, it may dispatch it opportunistically. It will run in the CPU until higher priority work is waiting and preempted. If it's not finished by the time opportunistic is done and the current time is reached, then it goes critical, and we saw that happen. Once it's critical, it's bound to the CPUs, and it's not explained in this manual, but miser work will never have pages stolen from it. vHand is not aware of the miser pool. Doesn't know anything about miser reservations. Okay. And ironically to me, this was what we called job packing 15 years ago when we were teaching COAS and stuff like that. I had a chapter setting up job packing concepts within NQS queues and stuff like that. This is software to do the same thing we were doing in Cray 10, 15 years ago. Now PS-C shows me my classes. So there's this class field. And each class has a different scheme in terms of how to schedule it, but TS is timeshare, RT is real time, B, C, and B were batch critical. I've got a batch critical code here, A.out. And a B is opportunistic batch, meaning it has not reached its critical time. And again, if you wanted to figure out, if you got that PID, so you do that miser underscore Q info, or J info. Miser underscore J info dash J and whatever that PID was, and it will tell you when it's going to go critical. At what time does it get its reservation? Okay. So if I did a miser J info dash J on 749.812, it would tell me when this thing's also going to end. The start time and the end time and the number of CPUs that it asked for. Let's see. So that's a little bit about miser. It's brand new software. We have several customers, traditional Cray customers, using it, and I cross my fingers that they don't have too many problems. One of the problems, as I mentioned, is a lot of these sites are using NQS to submit, but if the user kills the job, the reservation book isn't cleared up. I don't erase the reservation because the job failed. Once a reservation is made, there's no juggling of that schedule at all, no shuffling or repacking of it. And that's a critical feature. But NRL, Naval Research Lab, NCAR, Los Alamos, a lot of these key sites are using it. Now the next command we were talking about a little bit earlier was npry. Again, you require root to do a lot of this stuff, but npry can set a lot of these scheduling stuff on the fly. R can set the absolute priority for real time, so I can set it from 0 to 255. And S determines whether I want first in, first out, or timeshare. And N can set the absolute priority, or nice value, I should say. And rather than using slice size, a dash T can change my slice size on a per process basis. So I can take a real-time daemon, instead of saying 10 clock ticks, make it 100 clock ticks. Then instead of 100 milliseconds, it's actually 1 second or something like that. Less clock interrupts to that process. And again, these are more commonly used in the real-time market. Now there's also something called affinity scheduling. Let me go back to do for a second. Oh, shoot. To look at all this stuff again as a par-r. Since I'm going to do it, I should be root par-r. I'm going to put it into a file I'm going to call raw par file. And right now it's just collecting context switching and CPU scheduling information. I'm going to break out of it now just to end my interval. Now I can do a par-q on that raw par file and page it. And it now tells me what happened during the interval that I was looking at during the context switching. I had almost 6,000 context switches, CPU time slices. And for each CPU, I see how much time was idle, running, dispatched, ran on same, and ran not the highest priority process. So I get summary statistics. In most of these cases, I'm getting my processes off the local run queue that is per CPU run queue. And I'm not going to the global run queue, which is for real-time daemons. So we've got two run queues here. One is for my local run queue. That's how I get affinity. If my CPU frees up, I've got a linked list just for the things that are on my CPU. Then if I assign it, it's going to stay on the same memory node, and I don't have page migration or anything like that happening. Okay. There was a CPU here, for example, that did go to the global run 5 times to schedule a real-time process. Now, since I have that data, I can do a par capital RQ again, a more verbose mode. And now I can actually see what was running. For each CPU, here's the CPU number, and then it's got a list. In this case, lsdyna.latest is running PID of 130776 that's running on CPU 2. So I can see for each one of these things what the run queue length looks like. Now these are all lsdyna. Let me see if there's anything else of interest here. I didn't have a whole lot else running here at the time to compete. I've got some interrupt threads that are going on here. What I'm looking for, see in this status I've got one PID, another PID, and then I've got a whole bunch of CPUs that are idle, so I'm able to see what's actually running on each of these. I wonder if Irix view is, nope. Yeah, okay. As I mentioned before, Irix view is the tool, I know where I'm looking for. I've got a tool called Irix view, but unfortunately it's not on the mounted file system, so I've got to load the resources for it. There it is. Okay, and let's see if I can bring it up now. There's my raw power file. Bin. We'll get it there yet. Oh. There it is. Since it's not in my path, I had some problems finding it, but this should work now. But normally it's in user Irix view bin. And it's got some licenses that expired. I'll have to come back to it. What Irix view would do is actually plot a GUI and show me for each CPU the name of the process that was running on each. And it would actually drag and identify and basically visualize that par trace that I had before, and see everything that was running on a given CPU and what their time slices look like and stuff. With the license expired, I'm going to have to maybe load that during lunch and come back to that. Now, just getting back to the workbook, what I was trying to talk about was affinity scheduling and the fact that I've got a per CPU run queue, and that par-r collects the data about those queues, and Irix view can visualize it for me in a GUI format. And Irix view is new with 6.5.2. It's SGI written, and it replaces a product called WinView that Irix people have been using for quite a few years now in the real-time market. Now there is a parameter within the kernel called memory affin sched. I see no reason to turn it off. I've never talked to anybody that's had a reason to turn it off. But by default, we're going to attempt to keep a process on the same processor to avoid the traffic and to avoid cache pollution and avoid page migration problems. Reduces the need to flush the cache for a new process, and reduces the need to migrate memory by keeping it close to its CPU. So when a process gives up the CPU, either because its time slices up or because it's sleeping on some sort of wait chan event, one of three things will happen. The CPU runs the same process again immediately. The CPU goes idle, waiting for a week, or the CPU will run a different process. The first two do not reduce the affinity, but the third one will. If I see my CPU's idle, I'm going to look at the next CPU to see if there's work there, and if there's something there, I may grab it and move it to my CPU rather than go idle. Okay, which results in thread hopping, processes that can pop around in the system. So as long as the process has affinity for a CPU, it's dispatched only on that CPU if possible. When its affinity is 0, the process may be dispatched to any available CPU. And let's see what it's got here. IO-bound processes which execute for short periods build up little affinity. Because they're rarely being dispatched, they're rarely ready. And again, CPU-bound processes, we care about the affinity. And that's kind of what I was saying before. The more CPU intensive you are, the more it matters, because you're going to dirty up your cache more quickly. And LS-DYNA is an example. Right now, I bet LS-DYNA has both cache thrash and barrier synchronization problems occurring in the run that's going on with it. Now, I can also restrict a CPU, and this is for run-on. So Miser was a batch way of reserving CPUs and getting locked down in them. MP-admin and run-on is the more traditional way. So with MP-admin, I can do an R option and restrict that CPU, and then with run-on or the must-run capability, I can then lock down into that CPU. But all children, all threads inherit affinity to that same CPU. So I'd be competing with myself. So run-on only works in a single CPU, single-threaded type of application. So with run-on, I get the CPU attention 100% of the time, but I do still get clock interrupts. The involuntary clock interrupts do still occur, but nothing's going to get scheduled. My cache won't be dirtied by something else. Nobody else can pollute my cache. So I'm going to continually reschedule that process to the same processor. So in this example, mpadmin-R3, if I go back to my case, do an SU. mpadmin-S will first of all say whether I've got any restricted, and I do not have anything restricted yet. Okay, so everything, I've got all my CPUs 0 through 15, they're all unrestricted, and they're all preemptive. They can all have clock interrupts, time slice size behaviors forced on them. Now I'm going to do an mpadmin. And I'm going to don't take CPU 0 because that's your master clock and things like that. There's a restriction here. You also can't restrict things that miser has carved out. But I'm going to just pick 4. See if it takes my syntax. It did not like my syntax because I put a space in there. So I do 4. Now mpadmin-S shows that I've got one CPU restricted. Okay. Now I'm going to CD into where my workload is and do a run on for code 2 that I was running before. Okay. And I do a ps-l and I see that code 4 is in fact running on CPU 4. Now if I had a hybrid architecture where I've got 250 megahertz boards and 195 megahertz boards, and I am running single-threaded applications, then it would make sense to be able to use run-on and lock things down into the faster CPUs. Okay. The only other way I can target applications to multiple CPUs in the topology is a command called dplace, and dplace is unique to Irix. So we'll see how that thing's running here now. It's always running, there's no wait events going on, and it's stayed on CPU 4 because I restricted it and did a run on. But I had to be root to do it. Okay. So a run on was what I just did here, did a run on, they happen to use the same CPU number. Child processes inherit the same scheduling restrictions. It's used for single-threaded applications, but not for multi-threaded. For that, you use miser CPU set. Miser CPU set is like a pset. Okay, and with it, I can specify the CPUs that I want. And that's about all we have in that section there. So you will find daemons being locked down with miser CPU sets. I'll point out, though, that a miser CPU set shows up in the timeshare band. It will show up as TS. It will not show up as batch critical. So that's pretty much CPU scheduling. Do we have any questions before I get on? But there's a lot of flexibility with that mpadmin command. We didn't look at all the other options, but I can turn off clocks. I can change slice values on a per process basis. I can direct VME interrupts to a particular CPU where my interrupt handler may be locked down, things like that. And most of it's for the real-time market. Well, I don't hear any other questions yet. Maybe something will come up later. The next piece is called checkpoint restart. And we've had this in Unicos for quite a long time now. It was just implemented in Irix in 6.4. That was the first release to support it. Prior to that, checkpoint restart was done outside the kernel in user space. It was user support to do it. And it was a package called Hibernator. So Hibernator runs in user world and is able to checkpoint things and then restart them on a different machine. But we've moved that support into the kernel. So there's system calls to do this. Now, checkpoint restart is to save the environment of a running program so that if the system has to do a shutdown or we take a panic, we don't lose our work. Okay. And for example, NQS will automatically checkpoint work when it shuts down NQS. So if I do a controlled operator shutdown, NQS will checkpoint all the work, and then I can pick up from where I left off. I don't lose any work, hopefully. Also, NQS may do periodically checkpointing so that if the system takes a hang or a panic, I can pick up from a checkpoint image from a scheduled interrupt. So when I schedule it, it automatically shuts down and checkpoints, but I can do periodic checkpointing to protect against the panic, or machine just jumped into la-la land and is hung. We don't know what it's doing. Okay. So basically the checkpoint image is saved. The checkpoint image is also called a state file, and is saving all the kernel table structures as well as a.out, as well as any other resources that the process has associated with it. Shared memory resources, process table entries, credential structures, user table, thread structures, all that stuff goes into this state file. So the user asks the kernel, please checkpoint me through a system call interface, and then the kernel saves everything it needs to pick this thing up. This is one problem with Miser. Miser state is not kept. If I shut down NQS and restart it, all the Miser work will come back in the timeshare band. And that is a reported functionality feature request from customers like NCAR. So Miser work will actually lose its state file if it's checkpointed, which is a problem in a futures. So obvious benefit of checkpointing is to the ability to resume the execution of a process. Imagine the site that's running a program for 6 months, and 5 months, 3 days into the run, the system has to be serviced or it takes a panic or something. And Irix does not have the MTTI that we've had on traditional Unicos machines. So it's not uncommon for us to have interruptions once every couple weeks. A prime number finder may be out there running right now. We don't want to lose wherever it is in the next iteration of finding the next prime number. So that's what checkpoint provides us. It talks about improving load balancing and scheduling. The way they're doing that is with LSF and being able to, if a system becomes oversubscribed, checkpoint it to drop the load back down until the load level is suspended, then we can restart it. But it's really not being used that way yet. Basically, we do suspends, but we're not doing checkpoints. And LSF is the only product doing that. Runs complex simulations or modeling applications. Jobs can be rerun with new modified conditions. I can replace hardware with high availability by having the ability to take a service interruption and replace the hardware and pick up from where I left off. And also recover processes that may have been killed due to a paging environment. If I oversubscribe memory, Irix kills things. If there's a checkpoint image, I may be able to pick up from that last checkpoint image. Now, I don't care about checkpointing 5-second processes. Typically, it's things over 8 hours or more that you start caring about checkpointing. Okay, so the typical interactive user doesn't care about checkpointing things unless they have some major application that they're running interactive that they've got to force a checkpoint on.
Can you do a checkpoint, Dave, and continue running?
Yes. You can do a checkpoint without a kill. That's correct. NQS does that as a periodic checkpointing. Now, a word of warning about checkpointing in general. The system doesn't always know the best time to do checkpoints. If you're in the middle of doing a tape mount, it's not a good time to do a checkpoint. So a lot of the applications prefer to do their checkpointing because within the application, I know the best time to do it. I know what files, when I'm going to close files and things like that. If I have service sockets open across the network, like MPI jobs, those things cannot be checkpointed. So you can do a checkpoint and you keep running, but there's no guarantee that you're going to be able to restart because of some of these conditions. And if I restart and see all the timestamps on my file are newer than the restart image, then I know there may be a problem with my data. Now in Irix, I can specify what to do in those conditions, like append, start over, something like that. I think there'll be a slide describing that. So there are two methods, checkpoint and terminate, or checkpoint and keep running. So the state file is a directory containing all the information about the process, and the checkpoint process, or the checkpoint system call, is what creates the state file. Contains all information to enable recovery, but again, some information is not available in there, like where I am on a tape drive, where I am writing a CD, where I am in a socket connection on a network type of thing. I can't recover from everything. New processes should behave just as if the old process had continued without interruption. Again, another problem here is that I lose Miser, batch critical state. I come back in the timeshare band if I shut down NQS and bring it back up. And again, the state files are protected by normal security of user group IDs. So the checkpoint owner initiates the checkpoint operation through a system call. Only the owner or super user are permitted to perform the checkpoint. NQS is running as root, so it can do checkpoints for you. And only the checkpoint owner can restart. I can't pick somebody else's checkpoint file and restart from it. And if a super user performs a checkpoint, only the super user can restart it because of permissions. Slow here. Now CPR is transparent to the applications, but again, applications need to be aware of when's the best point to do the checkpointing, and that's where they start writing in checkpoint software to handle it. So you can save individual processes, process groups, the entire job. You can save job groups in the middle of execution and restart them later, assuming that restart conditions are appropriate. You can target processes running on a single system or an array of network-connected systems. So with an MPI job, I may be able to checkpoint the entire job across the environment. A job is a set of one or more processes. Again, a job is the same thing as a session or a process group. You can save the state of a job in mid-execution and continue or terminate. Then you can restart the job on the same system, move the checkpoint file to a different system in the same architecture, or do it on the same system with an OS upgrade. So if I'm going to go from 6.5 to 7.0 whenever that comes out, I can checkpoint everything, upgrade to 7.0, and then restart. Now whether that's tested or not, it's a whole other story. And in Unicos and even in Irix with NQS released, 9 out of the 10 test cases they had failed the restart. So they threw a bunch of stuff at the system. Capel did this. And 9 out of the 10 jobs did not restart. So it wasn't a very good success rate. But that's the intent.
Does checkpoints care about real IDs or
About what ID?
real IDs?
Real user IDs, yes. Both real and effective would be saved. The entire credential structure is there.
So it always starts at what you log in your parent process ID.
Right.
No matter how many groups you
Right. Okay, but anyway. So you can run processes across system shutdowns or OS upgrades, better management of resources, and it is integrated with NQE. We've got periodic checkpointing for unscheduled interrupts and checkpoint on shutdown. And by the way, the file system you're doing your checkpointing into matters, because that could impact your I/O traffic and stuff. Now there is a third-party package that's been used prior to 6.4 or 6.5 called Hibernator, and is only supported on IP 19, 21, and 25. And Hibernator is what LSF has been using for years. It's user space. It runs in the user world. There's no kernel support required for it. But then that creates the kinds of problems in terms of portability and that sort of thing. So beginning with 6.4, we added CPR. It's the future base for all SGI and Cray checkpoint restart products. It's got most of the Hibernator features, 40% or more functionality. Somebody else called that number, not me. It has a GUI interface to it, and it's supported on all SGI platforms. So I could checkpoint on one platform and move it off to another platform, as long as it's running the same checkpoint software. So this is just trying to show the CPR structure. We've got our process with text data stack going in there. We've got system state information, any page mappings, any signal state information, any files that are open. The files don't go into the checkpoint image, but attributes about the files do. And even on Unicos, if I did a file system backup and restore, my timestamps might be newer than my checkpoint file. So it comes up and says, well, the files are newer than my image. Maybe somebody's messed with them. So you can override that behavior and say, I don't care what the timestamp on the file is, just keep going. And all that information is going off into this check state file. The CPR command is how I can do checkpointing, and then CView is the GUI for it. We'll see a sample of that. You can look at your own. Security, it maintains your current UID, GID model. User can CPR only yourself. Root can CPR anyone else. And they're just going through a sequence here. Starts off with a checkpoint signal. kernel sends a checkpoint signal to the process. This allows each process to optionally catch the signal and decide what to do, and perform normal tasks prior to the checkpoint, such as closing files or something like that. Then we stop the process, save any open files and any other process-related information, save the process memory regions to the state file, and then either kill or continue the process. And then during the restart, we're going to create the process with the same PID, and there may be restart problems saying that the PID is being used right now or something like that. There was nothing to save the PID. We just hope we didn't wrap and happen to hit that same PID range. Then based upon the state file, remap the process back into memory and restore its initial states with the UID, PID, GID, all your priority levels, all that sort of information, all the accounting statistics, all your limits, your terminal activity, any sort of system call you were in, signal data, pipe data, shared memory, etc. All that stuff is restored. Reopen and restore any files the process had open, and then send a sig restart to the process to say go ahead and get started, and resume execution of the restored process. And when I checkpoint, I can checkpoint by PID, I can check by group, I can checkpoint by session ID, and again, session ID and ash are the same thing. I can checkpoint by the ash, and the ash goes across the whole cluster. An ash is the SID that's been negotiated the same for all OSs configured in the array. And with array services software, the array daemon, you say, here's the hosts that are in my cluster. And that could be Unicos and Irix machines within the same cluster. And then there's a HID, a process hierarchy. I haven't looked at that. And also by share groups. So you can specify, do those checkpoints by any one of those attributes. In this example, they've just got some checkpoints. They're checkpointing this process 1111 and putting it into a file called checkpoint mar2031. In this one, they're doing it with all processes having a group ID of 123, a hierarchy ID of 345. So basically, anything that's under the parent of 345 would get into this checkpoint file. Or by session ID, and again, the SID command prints out your session ID. And there could be a lot of similarities. If you're on the same platform, your parent ID, your HID, your SID may all be the same. Okay, it's when you get into arrays and multiple mainframes that they might start being different. And the last one, they're checkpointing all the PIDs and the hierarchy that's underneath all three of those PIDs. And in this example, they're doing a PS. They've got a program. In this case, it's the shell. So in 586, they're doing a CPR checkpointing the 25924 into that particular checkpoint file. He's then logging out. Now, I don't know that checkpointing the shell is that important. But he's logging out and then logging back in. And there does seem to be an error message saying that there's a .cpr file that's missing for attribute information. But then the person's logging back in and then doing a CPR-D on that checkpoint file and basically picking up from where they were before. Now, this is kind of a funky example using a shell. They might have been better firing off a.out and doing it with that. Let's see. Anyway, the user cannot remove the state file using the RM command. The CPR command is what removes the state file. And here's showing the GUI. So I can select, I'm not sure, I don't have the GUI here, but I could probably pick up multiple user IDs. It's defaulting to my own since it's running as user. And then under that user, I see almost a PS display showing the user and the other attributes that I have, including the ash, and then the name of the process. Then I can say check a process or whatever group, specify the file name, do checkpoint and upgrades if I want. And then there's some checkpoint options that are available in here. So they're doing a.out in this example, drills down into a.out and is saying the original process PID, I'm going to restart the job using that. This was C view, whereas the previous one was C view as well. Now the actual application interface, API, is a library interface called checkpoint create, checkpoint restart. And it's on that man page where you define the error statuses if I can't checkpoint, for example, file system full condition. Or I can't restart because the PID is being used by somebody else. Those sorts of problems. So I can create, restart, get status, remove the state file, or do a setup, which it says does not do anything on Irix. Now there are some system-wide configuration controls to control restart behaviors provided in ITSI CPR_proto. And in there we have an option, for example here, we're setting up a configuration file that's saying if these files, if I have problems with these files, in this case append the file or replace the file, ignore timestamps, or substitute. And then being able to continue or ignore if there are problems with the directory and things like that. So I have the ability of controlling options and saying, well, I know that this is a scratch file, go ahead and restart even though the timestamp may be bad on it. Or maybe somebody did a file system backup, remade the file system, reloaded it, and then the restart would fail, say the timestamp's newer than my checkpoint file. So then you can force an override of that and say, well, I know that it was just a checkpoint or a file system backup restore, so I can just go on anyways. Non-checkpointable objects, socket connections. I cannot checkpoint socket connections. Terminal sessions, can't checkpoint those. I can't do anything about special devices such as tapes or CDs. Files open with a set UID credential that cannot be reestablished when I try to restart. Maybe security has changed on the machine or something. And if I have semaphores or message queues, those are not going to be saved. And also any sort of open directories on the system or on the application. So those are some of the non-checkpointable objects. And I got about 15 minutes before lunch. I was going to finish up this section. And the last of this section is just on threads and libraries. We should be able to go through this real quick. A thread is a newer term in today's multi-threaded environment. And again, we used to call this stuff multitasking and call them a task. And actually the history here started off, in my mind, within Cray. Steve Chen gave us the first multi-CPU system, the XMP. And Europe, the ECMWF, European Center for Medium Scale Weather Forecast, was one of the first sites to buy this system and start using in what they called multitasking. Back in those days, when we referred to multitasking, there were task library routines that the application had to be written in. So they wrote their weather model and split the southern hemisphere on one CPU and the other hemisphere on the northern hemisphere on the other CPU. And then there were library calls, task library calls to communicate between the different processes, so to speak. They were fully independent processes. Nowadays, this has grown into what I'm calling multi-threading, since there are more non-Cray people out there than, Cray background. And multitasking in the general compute world just says that I can have multiple things running on my system. In other words, it's a time slicing operating system. Okay. Well, this has turned into what we now call MPI. And there was also PVM in here. So those library routines got re-implemented by our customers. PVM was done down at Oak Ridge. And then the MPI basically has been picked up by the University of Edinburgh out in the UK. And so these are environments where I rewrite my application and use library calls to synchronize events between the different threads. Okay. And this is when threading started becoming the name to call these things. Along the way then, we created what was called microtasking. And in microtasking, I basically put in compiler directives. So I'd go in and find my iterative do loop and then put a compiler directive in front of it and say, spread this iterative do loop across so many CPUs and stuff. But again, the programmer had to put in those compiler directives. Now that was less work than rewriting the application. Okay, so I let the compiler do my work for me. This has grown into what's now called OpenMP, and that is the industry standard now for microtasking. And the third thing was called macrotasking. And this basically said, let's put a preprocessor in front of it. In the SGI world, it was called the Power Fortran Analyzer, PFA. And this says, look at the source and automatically multi-thread it for me. I don't want to have to do anything with the code. I'm lazy. I didn't write the Fortran. Just do it for me. Let the software figure it out. Okay? And we have re-implemented that in prior releases. It was a third-party product license called PFA, Power Fortran Analyzer. But now the compiler has it built right into the compiler, and it's the Cray compiler that's doing this now. And it's in the back end of the compiler. It's no longer sticking. The older ones stuck compiler directives in your source. The newer ones don't work with the source. They work with the back-end executable that they're generating. So with the older PFA, you could actually see these compiler directives in your source. With the newer one, it's now called PFO, the parallelizing feature option. And I do mean parallelizing. The parallelization feature option, which tends to parallelize things if you did not go back and rewrite your application. And I found out just this week there's a utility called Parasol that will go through your Fortran and tell you whether it's going to parallelize well or not. And I've got to look and play around with that. But a lot of people are trying to use this.
You mean parallelize?
Parallelize.
Parallelize means like you can't move anything.
Yep. And that's what I mean. It paralyzes the system because they're spending all their time trying to synchronize barriers. And the application becomes paralyzed in trying to be parallel. So parallelization can lead to paralyzing you. Okay. And that is the number one problem, is that they will stick in a dash. This is automatic, so when I do my compile, I do an F77 or an F90 dash PFA. And then the software tries to spread it across the CPUs, but the synchronization is not efficient because the application is a 30-year-old Fortran not designed for a multi-threaded application environment. So I do mean parallelizing. And you will find applications out there. I also call this lazy parallelization because you're asking the OS to do it for you. When really what you need to do is go back and fix your application and look at it. And this is a common problem with NRL, Los Alamos, NCAR. They're all having the same problem, NCSA. If the variance in their service time is more than 25%, it's barrier problems due to auto-tasking. Okay. And again, the PE_environment man page tells you what knobs I can control to control these different environments. So a thread is basically a newer concept that came about when we started multitasking or multi-threading, spreading a single iterative do loop across multiple CPUs. And basic terminology is kind of a POSIX standard now, so it refers to an entity which follows an execution path in a program. So you may have a program that has multiple threads. One thread's doing one thing and another thread's doing something else. In Cray work, they're all working on the same array. They've broken the array into pieces and are doing a Fourier transform on it or something like that. But in other markets, for example in the network market, those threads may be doing other things other than iterative do loop breakouts. You may be firing off threads in the network area to do a variety of different things. It's one process with separate thread execution states going on within it. So when Irix creates a process, it creates one thread to execute that process, but then I may be able to expand that into multiple threads. A multi-threaded program may have several threads active at one time executing in the same address space. They can address each other's areas. They can all share the same data area in the same array. So one thread's working on one portion of the array and another thread's working on a different portion of the array. And threads share at least a part of their execution environment. They execute the same code and they deal with the same data spaces. But they're separate execution models. Each of them are basically in the older systems, they'll each show up as a separate PS. When I was looking at LS Dyna, there were 4 entries, which told me that that was a 4-thread application that was running at the time. And they'd all have the same parent process group type of ID. So threads are often also referred to as lightweight processes. What we did was we had this big process table and this big user.h, but in the threading model, every time I try to create multiple threads, I carry all that baggage around with me. So the threading model is to say, instead of having this big user.h, I've got smaller structures that are tied to the thread. And then every time I create more threads, I'm not carrying around the entire fork type of information that I have to carry around with me. I don't have to copy my open file tables and all these sorts of things because they're shared among all the different threads. So lightweight processes are threads within processes that schedule independently and can execute concurrently. And a thread is an independent execution state. It's a set of machine registers, a call stack, and the ability to execute code. And I guess that's the key thing. As you start threading, your call stack gets bigger, the stack segment. So if I have 128 threads, that's 128 call stack frames just for me to go one subroutine deep. And this is just showing that all 3 threads are able to address the same executable portion of code. But at some point, all those threads have to synchronize, and that's what's called barrier synchronization. So what are threads used for? Blocking. Application can make a request that may block, so I can fork off a thread and let the thread take the blocking. And then my other main execution portion could be off looking at networks, polling networks or something like that. Meanwhile, somebody has data come in from the network, so I send off a thread, the thread brings the data in, it's doing its own thing. Meanwhile, my original thread can go back to listening to the network socket. Okay. Now, traditionally, we're using threads to split up CPU work, but what I'm saying is a lot of the other markets, they're using threads to distribute network traffic and to do a variety of different things within the same process program name. Multitasking, when an application is multi-threaded, it may run on multiple processors simultaneously. And then in the programming area, applications are often structured into subtasks for modularity and simplicity. And threads can be dedicated to these tasks in various ways. And MPI is a threading model that basically goes across network boundaries. So MPI allows me to actually open up a socket and start forking off children on a different machine and spread my work across the entire data center configuration. So there are 3 types of threads. A standard thread is created by doing the fork. We then have the SGI model of thread implementation called SPROC, which is not the same system call as on Unicos or other vendors. It's unique to SGI. But there is now a standard, and it's called POSIX threads or pthreads. And pthreads is a library interface for multi-threading environments, whereas the implementation underneath may be unique from vendor to vendor. The standard for the library interface has to be the same. So it's POSIX defined. It's a Unix standard for threading models. But when you do man pages on it, you'll see that it's a library interface that eventually may be calling SPROC underneath it, or some other system call on other systems to implement that threading model. So it's called threads. So the earliest mechanism was fork. Within the Cray world, we created a couple other things. We created vfork and things like that to do our forking types of things. Basically, this is all replacing that sort of stuff. Now, SGI supports both SPROCs and pthreads, and pthreads are newer and being demanded by our customers because they're the only portable set of multi-threading. And there are other thread techniques out there. We've been using like mock threads for T3D. There's Solaris threads, R threads, C threads, things like that. So SPROCs are SGI's tried and trusted interfaces, and they're integrated in many of our products, so we still have to have SPROC there. But choose pthreads if you're re-implementing something because it's the threading model of the future, basically. But it does require you rewriting the application. So with SPROCs, XPROCs are the way SGI implements the lightweight process model. When an SPROC is created, it shares the various attributes with its parent. So it's got the same address space as the parent. So before SPROC, we've got a single thread is single space. After SPROC, we've got two threads, a parent thread and a child thread with separate PIDs, both of which are executing in the same thread of code, both of which have the same addressable data portions, stack portions, page tables, and U areas. And each thread will have a different PID, which is different than Cray. In Cray, you won't see the threads as separate PIDs. In SGI, you do. Okay. So with PS, if I see four things, that's four separate PIDs. They have the same parent. They're probably a multi-threaded application. And in Unicode, it doesn't look like that way. You'll have one PS entry for the entire threaded group. SPROC stands for shared processes. So it's just trying to show a layout here where I've got several processes that may actually share the same parent text. The parent has a different stack than the child, but the child is also able to manipulate the parent's data, run the parent's text, but they're going to have different stacks in this case. Child shares the data, is not a clone of the parent, and optionally the stack region can overlap, but typically is allocated separately. And there's also then something referred to as gang scheduling, and gang scheduling basically says that all threads are going to be connected concurrently at the same time. In other words, we're doing party line phone. And in gangs will be the first thing to collapse in the timeshare band. Gangs will not be allowed to connect concurrently. They will be forced into a single CPU. So P-threads are a portable model for the future. The POSIX standards defined out there. OpenMP is another standard. OpenMP is just microtasking directives, whereas POSIX threads are a programming model, a library programming model. So they're similar to lightweight processes made with SPROC. Preferred to SPROCs for two reasons, portability and performance. Now in the future, there's going to be something on top of this in the SGI world called Nano Threads. And I hope Nano Threads solve a majority of our barrier problems. Simple threads simply say, are you done, are you done, are you done? And your service time goes up as you're reading memory to say, are the other threads done? Dynamic threads says, are you done, are you done? Well, I'm going to give the CPU to somebody else and release it. Nano threads, to me, the best way to describe is saying, it's done at the library level, there's no kernel interface here, and basically one thread says, don't ask the other thread, are you done? Simply say, here's my CPU, get done. It's a way of passing the CPU to the other thread without kernel intervention. So if I get done with my work early, rather than waiting for everyone else to get done, I'm going to give them my CPU and say, get done. Here's a CPU for you to use. So that's three different levels, and nano threads are not supported yet. But I'm sure hoping they are soon, because that's ultimately what we need. The minimum amount of synchronization time. Instead of saying, are you done, and pinging and polling periodically, I simply give it the CPU that it needs and let it get done with it. And there's less overhead in that then. So you'll see a little bit more in the future about nano threads. And pthread_create is how we create the threads. So in this example, they're going to create two separate threads. They're going to execute a function 1 and a function 2. And then at the end of each of those threads, they do a pthread exit. So this is basically macro tasking again. We're rewriting the application, or writing it from the beginning. So pthread creates it, pthread exit destroys or eliminates that thread. And I think we're at lunch and everything, aren't we? So I'm not sure there's anything else here in the manual. What do we got for last page? Libraries. Well, you can read the rest of that, SPROCs versus pthreads. There are performance advantages to it. And I just want to wrap up here. The last thing we have are libraries. There are shared libraries. Shared libraries are shared text. Okay. And when you link them into a.out, the link editor, we've got different types of shared libraries. We've got statically linked unshared libraries, statically linked shared, and dynamically linked shared. The Cray world, we typically use statically linked unshared libraries. But the advantage of the other two is to save memory. Now, statically linked shared libraries say that every time I upgrade my libraries, the application will not notice it unless I rebuild the application. Whereas with dynamically linked libraries, all I have to do is load in new DSOs, and then the application will be able to take advantage of the newer DSOs. I don't have to recompile my third vendor application. And dynamic shared objects is the main model within the SGI world. Now, the advantage is that it saves memory and allows me to catch changes in the libraries quicker without recompiling and recertifying an application. And of course, the library interface has to remain consistent between the older and the newer libraries. It's got to have the same library call interface. So they're just showing a link of an unshared library, which is traditional Cray. We link it in and it takes up memory space. There's a copy of the routine multiple times. Whereas statically linked shared libraries, it's going to be when I build it, but then I can still go off to the shared library that's maybe sitting in memory and reference it. Okay. And then dynamically linked is during runtime. The entire library is mapped to the user's virtual space at the time of the run. And then when I'm referencing the library, I'm going to get what's actually on the system at the time of the run, not at the time of the compile and link. And that's it. So we'll come back and start talking about I/O 1 o'clock. And I'm a little bit behind. Okay. So I'd say that there are probably 90% of the customers out there that are running a -PFA using lazy parallelization and then trying to trust the system to set the defaults as best they can. And the defaults are designed for a single application, single user environment. In other words, simple works best when there's nobody else on the system. But if there's more than one person on the system, simple doesn't work, dynamic works better. And that default changes depending upon which library you've got. Okay. Are we going now? Okay. So that's the end of the CPU scheduling area. I don't know if there are any questions right now, but I'd like to go on with the file system. And some of the stuff will be new, some of the stuff will be old. The file system area is what manages our files and makes it user-friendly, basically. There are applications that do not use this stuff. There are applications that do not use the file system. Anybody think of one? They maintain their own file system structures and stuff. Oracle, Sybase, Informix, there are a lot of database engines that have raw partitions with no file system interface into the disk. Now, why would they want to do that? What's wrong with asking the kernel to do it for you? You're at the mercy of whoever else is in the kernel asking to do it. When it's within the Oracle application, it's its own boss and can make its own decisions without being affected by whatever political thing is going on in that kernel. Okay. The thing about the kernel is that a person can go in and abuse the system and hurt everybody else on the system. So all it takes is somebody to log in and suddenly Oracle has a problem if somebody is consuming all the buffers, for example, or using inode structures to find things. And it's going to be slower. In fact, a recent case study I was in, they're using Oracle for a news server and mail server, and all the articles and mail pieces are all becoming objects within the Oracle database. And that way they're not depending upon inodes per news articles and per mail message. When you send a mail to somebody, there's 4 inodes that go on in the system. Now try a storm of 100,000 email messages, somebody spamming your server out there, and you're getting a denial of service. So Oracle would not have that sort of situation of manipulating hundreds of thousands of inodes if we got a mail storm on a mail server, for example. But then Oracle's got its own problem of handling that load within it. But that's what it's designed for, lots of little transactions. So it avoids the file system interface because it can do better on its own. Okay. So in the file system management area, assuming applications are using it, it's user-friendly, interactive users use it. It's primarily database market that does not use it. And database market is lots of little I/O. Okay. So you got file access permissions, the chmod perm bits type stuff, file administration. File access coordination. I don't think there's going to be much here on locking, but being able to lock a file so that only one person can get to it. And this is an area that needs to be understood a lot more, particularly in the traditional Cray service person, is NFS locking mechanisms. Because we're in an NFS environment a lot more nowadays, and things end up spinning on locks that are NFS resources. And you can configure those sorts of things too. And then managing file integrity. And probably the biggest problem in file integrity is everybody's trusting a RAID 5 configuration to give them reliability of data, but there are trade-offs when you go to RAID 5. And primarily, RAID 5 is not designed to write data to. It's designed for large sequential reads. And we'll get probably into RAID levels a little bit later. Okay, I'm going to assume a lot of this is basic. The file system is a tree structure. Everything is based up on top as root. And then we've got directories going deep, that sort of thing. I'm assuming we've all got some Unix type stuff here. So it's a file system type structure. And a lot of this can map into DOS and other types of file systems as well. In fact, we can mount DOS file systems on Irix, things of that sort. And then in this example, they're showing where we're adding into the tree structure and mounting all their file systems. Each of these file systems has their own control structure and their own thread of logic to control what's going on in those file systems. Now, for whatever reason, they have lib mounted as a separate file system here, but typically that's not true in the Irix world. It's usually en route. But then they've got the user file system, and they've split that out. Some of the user file system is particularly important to split out, like var ADM, user temp, stuff like that. But in this example, they've got user bin mounted as a separate file system, and that's typically not true as well. So everything's starting off at root, and is basically a way to easily administrate and maintain the files. There's performance issues that have to be dealt with here. As we get larger and larger file systems, we have to be able to manage large amounts of data, not spend all of our time looking. And Irix does something different than Unicode. It's called a B tree, a binary tree through our inodes and stuff. And there'll be a little bit about that coming up. Also, it's nice to be able to reconfigure your file system dynamically while the system continues running. But in reality, a lot of situations will require a file system interruption, which usually means some sort of service interruption, unless you've got failover, where you can fall over to a different file system and run out of that, or fall over to a different system entirely for reliability. In particular, one of the issues here is fragmenting and defragmenting file systems. In our file system, we've got different types of files. Most of us are used to using regular files. That's the text, the data, the executable, things like that. Using the file command on the file system will tell you what type of file it is. And regular will show up as data. Then we've got the directory, which contains the inode information, and ls prints out directory contents. Then we've got name pipes, and NQS, for example, does use name pipes. The name of the pipe actually loads onto the file system with FIFO. And the qsub command basically opens that name pipe and submits jobs through it. So that's one example where a name pipe is used on Crays typically. And it's simply a file system path name to do I/O to a process's input, communication between processes. We also have special types of files in /dev or /hw. We've got character devices and block devices. And we can get to the block devices through a character interface. So we can read disk drives through block or character. But then terminals and tape drives are character only because of the nature of the type of device. And /dev/disk, for example, shows you the block interface. Okay. And when you build in Irix build file systems and volumes and stuff like that, you're going to get entry points for the volume name and stuff like that as well. We also have symbolic links. We can link within the same file system and save space, or we can do symbolic links across file systems. And there will be a little bit about that in here as well. And lastly, if you want to consider the files, network sockets. We can open up sockets to processes that are sitting on another operating system and communicate with them. And that could be considered a form of I/O. It's inter-process communication type of I/O. And then each one of these files has some sort of permission bits up here. We've got the user ID, the group ID, and what's called a sticky directory. /temp is an example of a typical sticky directory where you don't have to have permission to write into the directory in terms of ownership. So they're trying to show a regular file being represented here. Each one of these would be considered probably a byte offset, which actually gets broken into sectors. And the sectors may be put together into tracks that we're going to see, or whole cylinders worth of data. And each file has some sort of flat structure to it. We do support Unicode block structures on Irix, and the assign command provides us that capability. This is a flat file where it's all pure data, but you could have a file that has block control words pointing to the next block control word, indicating that the software has already sectorized the data into a friendly chunk that's friendly to the disk drive geometry, how many bytes to a sector or how many sectors to a track type of information. We'll talk a little bit about that. Typical into file is like a null or \n, or we could have an into file marking, for example, on tapes and stuff like that. And when we open up a file, they're just pointing out the offset starting off at 0. And a little bit later, we're going to seek into the file or position into the file. Now, the role of the inode in the directory is to find and map our location to the actual existence of the data where it resides out on our disk drives. So it's a friendly way for us to find our way to the data. But again, Oracle and database engines have their own maps and structures within the application to do the same sort of thing. And in the inode, we have a field within the inode that specifies the device that it's on, and we've also got an inode number within the file system. And from that, with the inode, buried in the inode, is a map pointing out to where the file's data actually resides on disk. And we're going to see a little bit later a command called Xfs bmap that will show you where it physically resides on the drive. Yeah? There's a couple places they're going to exist. They're out on disk, but they're also in memory. And with that gross view, they were part of that file system control data, or meta system data, along with directories and allocation maps. Okay, so now there's going to be a process we're going to talk about flushing it. So if we change inodes in memory, we have to flush it off to disk. So it resides in both places, and we have to synchronize that. And inodes is kind of a little older terminology. In the newer operating systems, they have a label around an inode we're going to talk about called a vnode. And a vnode is like an inode, except it's for virtual file systems, so I can point to non-Unix type file systems. So a vnode kind of points to an inode. An inode is kind of a subset of a vnode. But the vnode's going to be able to get us to an NFS path or a direct file system path or other types of file systems like PC. We can mount Macs, we can mount PCs as NFS file systems into Irix. And I guess the old terminology, inode, just comes from an index node. How do I index into the disk drives to find my data? So in this example, they're showing a link where we've got sitting in a directory actually 2 inodes. And the inodes are actually one pointed to the file and was created first, but the second one was probably added on with the ln command. And as long as they exist in the same file system, multiple inodes can point, multiple links in the directory can point to one inode and one data set. Okay. This can save disk space. Okay. But it also creates the problem that if I remove this link, it may still exist somewhere else. Your dumpster, for example, we may move it to dumpster, remove our inode information, but there may still be a link in dumpster that when we clean our dumpster, then it gets taken off the system. So the directory is the file that associates all the file names with the inodes. And in Unicode and in Irix, there's something called the Directory Name Lookup Cache, DNLC. Both operating systems have this. So that's where we go to get our directory names and then get to the inodes. There are some parameters to control that. There is primarily, for example, on a news server, it's not going to talk about it here, but NC size, a Z. that can control the size of that directory name cache, directory name lookup cache. So on a news server, we like to up cache as much as possible and up that and make sure that we use all of our memory as much as possible to control these inodes. And then we also slow down the flushing of those inodes to disk so we're not doing it too often since we've got so many inodes. News server is a very good example of that situation. And the directory name lookup cache is going to have multiple path sizes, and there are actually statistics available that will tell me whether I'm doing short directory names or long directory names, and have to do double lookups in the cache because I've got directory names that are real long path names, or real long character string names within the individual directory name. So using more than 16 characters, for example, could lead to penalties. Now this is actually breaking out the inode a little bit more. So we've got a directory where we've got the inode number, the name length, how big is the file name, and then the actual name of the file. And then that's going to point to the file's inode. There's a magic at the top, which basically is a sanity check. We look for a pattern there. And if it's what the pattern we expect, then we know that this is probably the structure that I'm thinking it is. Magic numbers are just a sanity check. So I say I expect a 1, 2, 3, 4 there. I look. If it's there, then I know that that's what I would expect. I'm okay. We also have then the mode bits that LS and Chmod manipulate, versions, formats, user ID, group IDs, the link counter, how many inodes, file names point to this inode. Project ID, in Unicode we call it accounting ID, but it's called project ID in the future. And with the Cray implementation, we're going to go with the SGI naming so that the traditional SGI market understands what they already have. So everything that's account oriented is going to be called project accounting or project type stuff in the future. There's also some empty space padding in the structure. Last time I modified the inode, the size of the file. There's a total of 64 bits for file size here. Something called generation number, I don't know anything about that. And then the actual pointers or dumpings of where the file exists out on the disk drive. And the default length of an inode is 256 bytes, but there's a command called Xfs growfs that can control the size of that. And hopefully if the file is small enough, it will reside inside the inode so I don't have to go further and further seek or position to get to the data. Once I've got the inode, I've actually got the data. And this is just showing that it's a typical 32-bit format structure for this file inode. The mode field, I think we all know about that. The chmod command is what manipulates this. We've got all these mode bits that give us access permission control to the file. First couple of bits is just breaking out the 16 bits. We can specify it's a regular file, a directory, character or special device. Like in dev disk and /hardware, you're going to see that type of bit set. And whether it's a named pipe. And then we've got a couple of bits, the set UID bit that says I can run it, I can change to the permissions that the file actually has, like a set UID program for root or for an entire group. So I can, if I'm in Navy, I can set the application to Navy and it's going to run as Navy rather than as myself. And lastly, the sticky bit that allows me to write into special directories like /temp, even though I don't own it. And then we've got our permission bits for the owner of the group and world, read, write, and execute. A total of 16 bits for that inode mode field. And with the ls command they've got here, we can see the file type is in the first column, and then we've got user, group, and read, write, execute for user, group, and other or world type of permissions. And the ls command is what prints out the names of the files in the directory. And with this ls command, we've got the file type, the permissions on the file. You may see like S's there for a set UID program. Number of links, how many file names in the directory point to that same inode. And you may have directories pointing to directories, so it's not uncommon for a directory here, for example, to have 27 links into it for the files that exist in that directory. Then we've got the user ID and group ID. If you see just a number instead of a name, that indicates it's not in the password file. It's not able to look up things with the NIS lookup or UNS lookup or something like that. Then we've got the size of the file in bytes. And keep in mind, this is only what we know about out on disk in terms of what the inode attributes are. If we have not done a sync yet, and the sync occurs like every 5-10 seconds, we may not see this right away. Also, we could have problems where the data is still sitting in our file system buffer cache and has not made it to the disk drive yet. The sync hasn't occurred, so this information may not be up to date. There are some people that have complained about that in NFS environments where I'm not synchronizing the attribute information quick enough to make decisions about state of the file and whether it's locked or not, things like that. Then we've got the default is last modification date, but there are LS options to look at the last inode modification or time created. And then lastly, the name of the file. And this is describing the move, ln, and rm command. These are actually done through system call interfaces. Okay, so there are unlinks and link type system calls to do some of the stuff. And this is showing a couple of inodes there where we're going to move a file, looks like link it, and then remove the second one. So they create a file or move a file in, creates an inode. Then they're doing a link, which is going to add a second entry in the directory to that file's inode. And then when they remove it, they're removing the second file's pointer, the second inode pointer, and we go back to a single pointer. The inode in the data does not get removed until we actually remove both entries in the directory. Let's see. And that's what it's trying to say here. An RM command may not actually remove the file depending upon what other links there exist to the file. Sticky directories, when the sticky directory bit is set, there is a T in the last field. /temp is an example typically of that. They've got a chmod example here where we're doing a 1777 to set that particular bit there. And this grants where users may need to grant write permission on their directory so that other users can do things in that particular directory. Temp is owned by root, but we need other people to be able to write into temp, for example. And then the set UID programs, we've got 2 bits to allow us. This is where we're talking about real versus effective. At login, I may get my credentials as a UID of 444, but when I run a program, there may be a set UID bit. It allows me to run the program as if I was that particular user or group. And actually in the accounting data, it will show up under the effective user ID. The typical example is root. There are a lot of commands that do a set UID to read dev kmem. Dev kmem is going away in the future, but there's still programs that do that sort of thing. So if you execute a particular file that has those sort of perm bits set, you're going to access the file as if you had the perms on the file. In this example, the executable was 888 for a user ID, so when I run the program, it's going to show up with an effective UID of 888. And that would also be what it shows up in the accounting data. And I can do it by user or by group. And this one, it looks like they're doing it by group ID rather than user ID. That's the only difference. Typically, it's by user ID. Now, to keep track of all these files when an application is doing I/O, it's got what's called a user file table. Basically, every time I open up a file, I'm going to get an entry in this file table. Now, the file table used to be in user.h, but now it's actually within the kernel thread structures. Are we having trouble finding the page? Did I skip a page? Okay. Saw too many people thumbing through. Now, when you actually start a process, it typically has 3 files open, standard in, standard out, and standard error. What we've always known as the file descriptor is basically the index into this file table. Okay. And we have the exact same thing on Unicos. And this is also pointing out that we do have a limit. We can control the number of files that we can open. And for a long time we had a limit, even in Unicode, of like 60 files that we could open at one time. So now there's a default where we can control the size of that table, basically. And there are applications out there. The record I heard of was University of Bergen out in Scandinavia was opening up, one application was opening up 1 million files. Okay. Maybe in the weather market, you may be opening up 1 file per day or something like that. You may have 3 files per day. 1 for pointer information, 1 for summary information, that sort of thing. So you can get a lot of files opening up in a typical, not a typical, but the unusual applications. Most of them don't open more than 5 or 10 files typically. Now this file table is not directly accessible by the user program, but we can get to it through /proc. /proc is a way of looking at the process image just like it was a flat file. So we are able to read some of this information out of /proc, but directly we cannot get to it. So every time I open up a file, even in Fortran, every time I open up a file, I'm going to get an additional file descriptor added on. Now in that file table, I keep track of information like the open flags. Is it read, write, execute type of permissions? Where is the inode? So I've got a pointer to that. User reference count, how many references there are to it. The file offset, where I am in the file if I'm concatenating a file together, and then the number of bytes that I'm reading or writing. And this is pointing off then off this system file table entry, just showing that we do have a pointer in there going off to the file inode. And this occurs every time a process opens a file. Now when you do like prints or something like that, there's an open being done by the library routines, libc or whatever, that you're calling within it. And again, the reference count maintains a count of the number of user file table entries associated with a particular system file table entry. Typically it's 1. When you close a file, the reference count goes back to 0. If the counter is reduced to 0, then entering the system file table is released. No more files. Oh, there was one other thing in here. Positioning. Random I/O is done by LSeeks. So database engines, for example, will be doing a lot of LSeeks to position into their data. Sequential I/O will not have these LSeeks going on. We just do reads and writes. In the Fortran world, for example, I may do a write off to unit 5, and I will specify some sort of format string saying I'm going to write formatted data. If I don't have that, then it's unformatted or raw data. But then at the same time, there's another type of Fortran I/O where I can say write, comma, and then do a rec equals and specify the record 10 is what I want to write to. Okay, and that would be considered direct I/O or random I/O where I'm positioning into the file and doing different things. Chemistry codes do this sort of thing as well. And again, PAR is going to show you this sort of stuff. It'll show you the LSeeks going on to position yourself into the file. And in a random I/O environment like a database engine, you may have a lot of LSeeks and high system time just due to this positioning. Okay. If I'm doing Vi, if I'm in Vi, if I'm on a 100 meg file and I go from line 1 to line 10,000 or something like that, I'm doing a position into the file. I'm seeking into the file. I'm not concatenating through it. So the user and system file tables were shown here, a user file table with standard in, standard out, standard error, and they apparently opened or did a print into something called my file. And standard in, standard out, standard error showing us a reference count of 3 for those, and then a reference count of 1 for my file, and then we're just showing the file table pointing off to the actual inode for that particular file. And keep in mind that the standard out, standard in, and standard error are basically the device terminal as far as the shell is concerned. And in this example, we've got 2 processes now. Second one seems to have opened the exact same file as the first one. Entirely possible. There's no locking by default on a file. You have to explicitly lock a file. For example, I could have several files, several processes writing into the same file, writing output into the same file. And it gets rather hard to read the file if you don't properly synchronize it. So this is showing two files, pointers, pointing off to the same inode. Talking a little bit about a fork. And I'm not sure this is anything different. So it's just going through the process where user A opens the file called my file, and then another process, user B, opens the same file that had already been opened, my file, a previous time. Well. So following the open process, when you open a file through the open system call, a file is located in the tree structure. After the file is located in the directory information supplies the location of the inode. We then get the access permissions located in the inode to check to see if we can go further, have permissions. We then create an entry in the system file table for this open request, and then an entry is created in the user's file table in user.h type of structure, in the user thread structure. The user file table entry is linked off to the appropriate system file table entry. And we link the system table off to the inode. And then the file status flags in the entry are set indicating the type of I/O it was opened for. Are we opening for reading, writing, both? Append? Can we append to the end of the file? If I use I/O redirection with 2 greater than signs, I may be appending to the end of the file and positioning to the end before I do my I/O onto it. And then the index to the particular file table that we opened, the file descriptors, return to the user process as a result of the open. So I open a file, it does all this stuff, and then returns the pointer, or the index, or the file descriptor. And then closing a file does the opposite. The file descriptor is located in the user file table. From there we get to the system file table. From there we get to the inode. We have an in-memory inode that has a counter maintaining the number of processes that have that file open. So we drop that down, determine whether the inode can be released from the inode table, and then it attempts to discard or get rid of the entry in the system file table. It checks for a reference value greater than 1, saying that more than one person has still got that file open. If not, then down at the end, the entry is going to have to be removed and the space is given back to a free list. At that point, the user file table is removed, making the descriptor no longer valid, and then any sort of buffer space that was being used for this I/O is released. In this example, they're saying that the actual I/O occurs sometime later. I think they were doing a read rather than a write, which means it's going to get released right away. And actually, it will go clean to dirty 100 seconds later, or I'm sorry, clean to inactive 100 seconds later. It'll just get marked as an inactive file. And as long as there's no memory pressure, if I go back to that file, I'll still have it in memory. We're going to get into the file system buffer cache in the next section. Now with the shell, we can do I/O redirection. So in this example, instead of going to the terminal with standard out, we're using the greater than sign and putting the output into a file called output. And in this case, they're opening up output. It's got a file descriptor 3, but it's actually being copied to standard out's position in the files table, in the user file table, because the application is expecting 0, 1, and 2 as your normal I/O redirection file descriptors. You know, when you're using the shell environment and everything, you can specify the file descriptor number, 0, 1, 2, that sort of thing. So they've got to make sure that if we do I/O redirection, we put them back into the slots in the table for people that do specify by file descriptor. In the Bourne shell, I'll often do a 2 greater than to redirect standard error, for example. Whereas in the shell, C shell, I have to do greater than ampersand sign to redirect standard error. Anyway. Library level file management. We also have this file structure for the libraries to manage things, which actually is pointing to the data sitting in user I/O buffers. Now this is a space within a.out, within the heap, within VSS space, within the data segment of the process. So whenever I'm doing I.O., I typically have a library in between. Now if I do opens, reads, and writes, there's no library. But if I do printfs or write formatted statements or do Fortran, there's a library in between. So this is not part of the kernel structure or system call. This is part of the library interface as I make library calls that do I.O. So if I do a printf type of thing, I'm going to get this file structure created, and it's got information about this thing called a user buffer. And for those people used to Unicode, the assign command allowed me to control the size of this user library buffer. Okay, it was like 48 Cray blocks by default. On Irix, it's 4 kbytes by default. There is a library call named setBuff that allows you to increase the size of that library buffer. For example, if I'm moving a terabyte of data, I don't want to do it 4 kbyte at a time. I'd like to increase the size of that buffer to like 64 kbyte. And this is something you should know about with Irix. 64 kbyte is the friendly number to do I.O. on. Everything is keyed up as 64 kbyte as your defaults. File system buffer cache chunks all of its data in 64 kbytes. Default stripe units are in 64 kbytes. The hardware caches within the disk drives are configured into 64 kbytes by default. And Mountain View and engineering simply said 64 kbyte is my middle-of-the-road compromise between the low-end database stuff and the high-end video streaming or data streaming type stuff. When you really get into tuning, you need to understand which direction you need to go and change those. 64 is just a middle-of-the-road. In the database market, we can drop all that down to like 4 kbytes. And in the video market, we try to increase it up to like a video frame size and figure out when I'm doing I.O. how big is a video frame and make these buckets, these buffers, all the same friendly number so that when I'm moving data around, I don't have to break it into pieces and put it back together and things of that sort. The same thing's true on Unicode machines. For example, the new iOSs, the iOS Vs and Fs and stuff like that, block our data at 32 blocks. It's hard-coded into VxWorks. But our I.O. libraries are still set to 48 blocks, which means I'm going to take a 48 block transfer. This is Cray 4K blocks. Send it off to the iOS, and the iOS is going to take 32, 16, 32, 16, which means we're basically wasting 25% of our bandwidth because we're not filling up the buffers all the way the second time. So we go through all this protocol to move our data around. We want to make sure these buffers, these stopover points for our data, are all whole friendly numbers of these friendly geometry questions. And we either pick the geometry of the disk drive, like sectors to a track, or we pick the request size of the application. Like in the video market, video frames are a certain size. So all the I.O. is going to be done in a certain size. We'd like to be friendly to that. And we're going to come back to that a little bit later. But this user I.O. buffer, its purpose is to hold the data before I actually ask the kernel to do it. That way I don't have to tell the kernel to move me 1 byte at a time. I pool it together into this buffer, make it a worthwhile transfer, then I tell the kernel, here's my I.O. The worst thing in the world would be to move a terabyte of data 1 byte at a time, one system call, and do a terabyte system call type of thing. You'd like to get those into big chunks, as big as you can get them, and then send them off. With XFS, 64 kbytes the default. Unfortunately, with NFS, 32 kbytes the default. So that means when I'm consuming memory, I may do a 32 kbyte transfer for NFS traffic, but actually consume a 64 kbyte footprint in my memory for that particular file that's coming in. So you end up wasting memory and stuff like that. So this buffer, the assign command is how we can manipulate it in Fortran, and the setBuff library call in the C environment to increase the size and get it to a whole friendly number. And 64 kbyte is the best, or whole number multiples, 4K, 8K, 16, 32, 64, 128, 256. 96 kbyte would be a bad number because that'd fill up one buffer and then half of another buffer. And then you're wasting, I've always compared it to the fire bucket brigade. If I'm going to fill up the bucket of water, let's fill it up all the way before I pass it down and make it worth the effort of moving the bucket down the fire bucket brigade. So these I.O. operations are typically at 4 kbyte in size by default. On Crays, we're much bigger, 8, 32 kbytes is what we use on Crays typically as our default library buffer size. So whenever I do prints or something, I'm going to have to do an open from the Fortran, for example. It's going to create a file structure. The file structure is going to point into the file, and then I got byte offsets into the file where I am, where's the start of the file, any sort of IO flags and locking, and what's my file descriptor. How do I get back to the open so that I can get back to the inode itself? And by the way, increasing the library buffer size is going to increase user memory space. It is within user memory space. And with a sign command, instead of making that a buffer, I can make it a cache. We used to call it EIEIO. Anybody hear that? Old McDonald? The EIEIO layer was written for things like Nastran that do predictable sequential I/O. And therefore they can cache. And now we're caching in user space rather than using the kernel to do our caching. And then nobody can pollute my cache because it's mine. Of course, I pay more memory for it. It's going to take up a memory footprint, but that's a trade-off you have to make. There are things called out-of-core solvers. How many people have heard of out-of-core solvers terminology? Nastran, for example, is an out-of-core solver. An out-of-core solver is written for situations where we know that the data set's always going to be bigger than physical memory. So we're turning a memory shortage problem into an I/O problem, and we're going to manipulate our data in pieces. So for example, Nastran, we take a CAD program of a car, we break it up into a grid. You've all seen what those grids look like. We then run the grid through Nastran, and the grid, each individual grid will have a modal analysis done on it, and then they can look at the vibrational properties of this particular car. And each one of those particular grids is an individual calculation matrix that we run this algorithm on. Now, Nastran being an out-of-core solver, there's a lot of data to that grid. So we know realistically the finer my grid mesh, the more data I'm going to have, for example. So these out-of-core solvers are designed for that scenario. So they read the data in pieces. And then they use memory to work in, but they know they can't fit the whole thing in memory. Now, Nastran is a prime example of an out-of-core solver because it's got two knobs on it. One is to tell it how much memory there is on the system. You can give it a clue and say, I'm on a big system, and you can up this library buffer size and say, I'm on a big memory system, so there's a Nastran command line option that says, increase your scratch memory space. Then I don't have to do as much I/O because I can pull bigger pieces of my program in. But I'm still an out-of-core solver because maybe the programmer is going to do a coarse model first and maybe say, let's shake the car at 1 foot grids and then go to 1 inch grids, something like that. So they can run a coarse run of the simulation and then go to a finer grid, and that's going to take more data, and that's why you need it to be an out-of-core solver. So by telling it that you've got more memory, you can reduce the number of system calls and reduce the overhead of the I/O at the expense of memory, but that's to your advantage if you've got lots of memory, and you've got to find the trade-off there. The other thing that Nastran can do is tell it what should the request size be. Now, in the Cray world, Nastran does its I/O direct to disk. It does not do it through cache. And what we generally try to do is match stripe width to the request size of the application. So I can tell Nastran, do a larger request size, and then I set the number of drives and the stripe width of my file system to match that request size. But with cache in between, that distorts the problem, because it's going to break it up into pieces again. Now we'll come back to some of that sort of stuff. Let's see. So this is just showing the library level file management where we have file structures pointing to the user file table, and in the user file table pointing to the system file table, and off the system file table pointing to the actual inode itself. Okay. The next piece is on disk basics. I think a lot of this is real old for us. One of the things that has happened in the past 10 years, though, is we've gone to disk drives that are called zone bit drives. It's not talked about here. Zone bit drives have different geometries on the outer tracks versus the inner tracks. There's more sectors per rotation because there's more area that we're covering. The original drives that Cray started off with were not zone bit. They had the exact same number of tracks per rotation. And we had a lot of applications that were written out there like disco, petroleum sites, and stuff like that, that wrote to the magnetic peripheral drives that we were originally shipping with Cray 1s. And a lot of them have not been updated to write to newer types of drives. So this is just trying to show a disk drive, but it looks like this is not a zone bit drive because the axials that's shown coming out here give me the same number of sectors per rotation, no matter where I am within the drive. With a zone bit drive, I've got less sectors on the lower track numbers, and this portion of the drive is more latency portion of the drive. If I had to split a drive apart, I'd like to put all my lots of little I/O in there and put my large sequential out here. And there's an example of that, which is your root device. With your root device, they changed things such that the swap partition and the root partition swapped around in 6.5. And they put root on the faster portion, latency portion of the drive, where I can do lots of little I/O. That was good. They also moved the swap portion further out on the platter, which put it on the bandwidth portion of the drive. And that's good because in swapping, we need bandwidth, not latency. Now, they did not do this intentionally. It was done for RoboInst, to be able to run RoboInst within that raw partition area. But the trade-off was that they got performance advantages out of it as well. One of the things that I try to do when I get a particular system is figure out what the characteristics of my disk drives are. How are they put together? What are their geometries like? How fast are they? How many tracks? How many cylinders? How many sectors per track? I also need to know things about how they sync up the spindles. A lot of these drives are designed for video streams, and they will sync the heads together, which is good in a streaming situation. But if I'm doing lots of little random I/O, I want to turn off spindle sync. Okay? And it's not uncommon for me to have case studies where somebody goes to a site, they've got it configured as a RAID 5 cabinet designed for bandwidth, designed for video streams, and they're doing a database application on the thing. And it was the wrong drive. They sold them the wrong drive, but you basically take that RAID cabinet, split it up, reconfigure it into narrower stripe groups and stuff like that, turn off spindle sync, a few other things, and turn it into a database drive, not a video drive. Now, if you're in the video market, this new command called disk align will actually give you recommendations on stripe widths and stuff like that for the video market. But there's nothing there for the database market. And it's going in the exact opposite. It will set up your drives for bandwidth, not latency. And we'll talk a little bit about some of that. Yeah?
I'm a little confused when you say spindle sync. My understanding is that spindle sync is only used in parallel RAIDs.
Well, I'm saying that may be on it. In this case, it was a reciprocal drive where we had to turn that off. You're right, there's a lot of different drives, and my first question is, what are the characteristics of this drive? And I was extending it into a case study that was actually a reciprocal drive where we turned off spindle sync.
So reciprocal has the ability to maintain a parallel RAID device without having spindle sync?
Correct. Yeah. And we did this on a secret site up in Canada that was running a database market, but they'd been sold a bandwidth device. Okay. But there are other things that go on in there too, the firmware controls, the caching behaviors and stuff like that that also have to get set up. Command tag queuing. Command tag queuing is good in lots of little I/O, but it's no good in video streaming. It allows, command tag queuing allows a busy bus for you to get commands across the bus and let the device on the other side queue them up. That way when they need a command, they don't have to wait for bus arbitration to get the command. But in a video streaming environment, you don't want command tag queuing. It won't help you at all. It may hurt you. And support people and salesmen have to understand these two situations. They're completely opposite ends of the spectrum. And the worst scenario is on Cray sites where they're doing both in the same file system, where they're running large sequential applications like Nastran, and then they're running random Gaussian applications in the same file system doing lots of little I/O. And they step on each other and they interfere with each other. And that's where sites get into separating their file systems out. So I'll create one file system for random and another one for large sequential, things like that. At some point, too diverse of an I/O workload is going to cause problems. And this is what our animation sites are having a severe problem with. The DreamWorks and Pixar's and Disney's and stuff like that, they're doing diverse I/Os into a single RAID 5 that's designed for bandwidth, and they're doing everything possible into that file system. And oh, by the way, they don't want to spend money on disks, so they're running it 95% full. And I don't recommend running file systems 95% full. And all of that creates a problem. And it's all NFS mounted, so all it takes is one congestion on one of these files, and everybody in the data center comes to a halt because they're all NFS mounted. And just CDing to $home and doing an LS does I/O to that NFS server. So the first thing when you get to one of these systems is to figure out what the characteristics of your drive are. Now the core origin product line is 2 drives, the Seagate and the IBM. They're the same drives we've been using on J90s, but they're formatted differently. Okay. And the IBM drive is good at large sequential, the Seagate drive is better at random. However, the IBM drive, we've got what's called thermal compensation on the drives to be able to adjust for temperature variances and stuff like that. The IBM drive does thermal compensation scattered among the heads. It doesn't do all tracks at once, where the Seagate drive does the thermal compensation for all heads at once, which is bad in the database market because now my entire head setup is busy trying to realign to the changes in the geometry of the drive as temperatures caused it to expand or contract. So in some cases, you've got a better drive for database, but now you've got to live with the trade-off of this thermal compensation. But the IBM drives are typically better at large sequential, like the video market. Seagate drives are better at the database market. I don't know if it's going to get into it here, but we're just showing the disk platter here. A track is a single rotation on the platter, broken into sectors. And again, Cherokee.Inger is where I go for all the attributes about the different drives. And you know what another problem is that's going on here now? Bigger drives. Now why is that a problem? Because I can't fan out my data. In the database market, they can't get the small 2 gig drives, so they'll buy a 4 or 8 gig drive and throw half of the drive away and only use the latency portion of the drive. As we get these bigger and bigger drives, that just means there's more data there and more contention for the data. And I'd rather have 4 gig drives than 1 18 gig drive because I can fan out my I/O among those 4 drives. If I put them all into one drive, I can't distribute my I/O anymore. And a lot of these customers are buying the bigger drives and not buying enough of them. And then they're becoming I/O bound. And this is the problem nowadays. The CPUs are pretty fast, but now we're choking on I/O. We're choking on cache, we're choking on the disks, we're choking on the networks. Because the CPUs have caught up to everything else. And the amount of data that we're moving around now is 100 times more than was 10 years ago. Particularly across the internet with meta documents and multimedia and everybody mailing frame documents to everybody and showcase and all that sort of stuff. So I generally go to Cherokee.Inger to look up the attributes of my particular disk drives, including quantum drives or other third-party SCSI types of drives. And that is tuning information that I want to take advantage of. Now a cylinder then is all the tracks at the same platter location. It's a slice through the tracks going down. Looks like a cylinder. And then a partition, which is different than Unicos. A partition is a slice or a contiguous group of these cylinders. And we're going to partition our drives out, but a Cray partition is more like a volume element within Irix. If you need a comparison, a Cray partition is a volume element, whereas this is simply breaking up our drive or partitioning it out. So a partition is a contiguous block. There's a command called print vtalk that will print out your partitioning. And yeah, recently we specified things in terms of blocks, not cylinders or tracks. Now there are several partition types, and this is where we are very different from Unicos versus Irix. In this area, we have what's called a volume header, and the volume header is basically a way of knowing what's on the drive. We then have our XFS data. Now, there is an older file system called EFS. That's obsolete. It's going read-only in the next release. I'm probably EFS on the workstation. EFS does not span more than one disk drive. It is a faster file system, but it's not designed for production multi-device file systems. So XFS is the only file system you're going to see in the future right now until the next type of file system is put out. So all the data, when I create files, all the data within my file system is going to go into the XFS data partition. Okay, that's where my actual data resides. Now, in this case, they're actually putting what's called a logical volume data stream. XFS is the umbrella under which the logical volume is a subset of it. So XLVs are the way I put my partitions together to create stripes and mirrors and stuff like that. Okay, so those are two different layers. XFS is the big layer, which includes file system buffer cache. But underneath it then is the logical volume manager, XLV. And that's what controls striping and mirroring and distributing the I/O across the disk drives. We also have something called a log. And the XFS log is to recover the file system control data if I corrupt it. How many people remember GenCat, or how many people have been to Saudi Arabia with a very large file system on craze? It takes half a day to rebuild the file system if they take a panic. And how many people have gone through a startup of a file system and it keeps complaining about all these orphaned files? Those orphaned files means that the tree structure, all these pointers between inodes got corrupted for whatever reason. So on craze, we always rebuild that linked list, the directory information, when we boot the system. In Irix, we have this XFS log to keep track of the changes, so if we do get a corruption, we can go to the log and rebuild the links. It's more quickly. So as the system scales larger and larger, it's more to our advantage to go to a log mechanism. Okay. If it's a real small one, we're better off with the way Cray did it because it's small and I can rebuild it more quickly. But as the system gets larger and larger, that doesn't scale. Try putting a tree back together and all the leaves back onto a tree after the wind's shaking them all off. That's what GenCat and those things were doing. Okay. So this XFS log is for reliability of the file system pointers, but not the data itself. I still have to either back up or use RAID to protect the data itself. Okay, it's only protecting inodes and bitmaps and the meta control structure information. And by the way, in 6.5, you can turn that stuff off. Now, I typically do not advise that. The only time I advise it is if PS-L shows you you're always waiting on the XFS log lock. Okay, and that rarely happens. I have not seen this to be a performance problem on any site directly. And we're going to come back to logs in a few minutes. But I can control with 6.5, I can control the size of that log, and I can also control whether I do logging or not. And I guess I should point out now that log can exist in three ways. Internal. And it doesn't show it in the workbook, but when it's internal, it's in the middle of the drive. Okay, so I basically have the log in the middle with, for example, root on both sides. And we went through this in Cray as well with primary and secondaries. I've been out to NASA Goddard, and they put the primary in the middle and the secondary in each side for like temp. Now what's the problem with that? They did this thinking, well, the log's always halfway. I'm always at least halfway from the log. But what's the problem? My data is now end to end. Which am I doing more? If I'm doing lots of data streaming, I don't want my log in the middle. I want my log at the end. Okay. And I saw this on Craze as well. Unfortunately, in Craze we track cylinders crossed with SAR-D. In Irix we don't, so we don't know how much shaking the drive is doing. Okay. But on Craze you could easily spot these drives because cylinder crosses would be way out of range because it's always spending its time positioning end to end on the drive. So when it's internal, it's in the middle of the partition. When it's external, I repartition the drive. And where would I want to put it? At the beginning of the drive or the end of the drive? 0 to max. Where would I want to put the log? What's the nature of the I/O in the log? Short little I/O. So I'd rather put it at a lower track number because it's on the latency portion of the drive. Because the inner tracks are better for random I/O, lots of little I/O. And the outer tracks are better for the bandwidth. And then I can put root down here.
If it's a zoned drive.
True, but all the drives we're working with now are zone drives. Even the Data General RAID cabinets are IBM or Seagates in them. Okay. But yeah, it's just going back to the geometry. But the point is that if I do split out that log and I do have a variable geometry drive, I want to put it on the portion of the drive that's designed for lots of little I/O. Now, in Unicode, we got the same situation with primary, secondary partitions. If I've got two different disk drive types, I want to put primary on the lots of little I/O type of drive, and I want to put secondary on the bandwidth and the RAID devices. And unfortunately, there's a mechanism that's been lost in history here called the crossover point. Anybody ever hear of the crossover of the drive? We used to document it, but then when zone bit drives came in, we couldn't compute the crossover because it was variable geometry. But the crossover is basically bandwidth times the seek plus the latency of the drive. Now, if I start striping drives together, the mechanics underneath will have the same seek and latency. I'm just banding them as a RAID cabinet or a stripe group. But what's going up is the bandwidth. And that's why I stripe, is for bandwidth. So the crossover is going up. So if I had two different drives, I can derive this crossover. If they're all the same drive, it makes no difference to me. But if I've got two different drives, I'm going to take and derive this crossover. And the one with the lower crossover I want to put on primary, or lots of little I/O, or Xfs Log type of stuff. And then the secondary would be more towards the bandwidth side. The one that has the higher bandwidth would be where I put into the secondary partition, or where my actual data is going. So understanding the nature of the I/O helps you target these things properly. And that's the problem, is we get a RAID device that's bandwidth driven because we've striped them all together, but then we're doing a 4K operation off of a database. And if it's credit card transactions, I can't up the size of the request because there's only so much data to my credit card transaction. So I've got to drop the geometry of the disk drives down, drop the geometry of my striping down, drop the geometry of my file system buffer cache down when I mount the file system. All those sorts of things.
David, is this similar to what we used to do in Unicode, where you'd have multiple slices for a file system and you would assign different big blocks?